Hi, good morning, everybody. Welcome to the webinar. I'm just going to wait another couple of seconds, see if we find a few more people joining us, and then I'll be playing the video. Today's webinar covers logic simulation when using the IEC 61131 languages in the OCS. So, as I say, a couple of seconds, and then we'll get started. So, away we go.
Welcome to today's tutorial. Let's get started. Let's look at today's agenda. We'll start with a review of the Seascape logic options. We'll talk about our standard IEC languages and our enhanced IEC languages. We'll discuss the features of enhanced IEC, including logic simulation, variable setting and monitoring, and setting breakpoints and trace points. As always, we'll finish with a live Q&A session. Let's discuss the Seascape application development process. Seascape is used to configure every aspect of the Horner OCS all-in-one configuration tool. Within Seascape, you can configure the logic programming, the I/O configuration, the operator interface development, and the network configuration. You have multiple options for what form of logic programming you want to do. You can choose between register-based advanced ladder, variable-based advanced ladder, and IEC languages. With register-based advanced ladder, you need to map your variables to specific memory locations in the controller. With variable-based advanced ladder, most of the variables you create do not need to be mapped to specific memory locations. Exceptions to that include real-world I/O and some communications type variables that might be mapped to Modbus or something. IEC languages are the standardized set of 5 IEC languages, including ladder logic, structured text, function block diagram, sequential function chart, and instruction list. Although in 2017 the IEC declared instruction list as deprecated or discouraged from use. Standard IEC has been available for many years, and it's compatible with all Horner controllers. It's limited to 10,000 variables, and it's executed at a slower scan rate than advanced ladder with the standard IEC. We have a relatively small but growing loyal customer base. It's growing because you're able to choose different languages for different parts of the machine logic. A lot of new engineers especially like to gravitate towards structured text. Enhanced IEC is newly available with Seascape 9.90 Service Pack 4. It's compatible with the X5, the XL4 through to the XL Plus 15, and with all RCC models except for the 6512 high-speed coprocessor. It's a licensed product. You're no longer limited to 10,000 variables. We can support 64,000 variables, and there's no longer a performance hit. There's a host of new features too, including online programming so that you can change the program in the controller without stopping the controller. There's the simulation feature that we'll cover in detail. There are additional data types like enumerations, improved exception handling, and a whole bunch of other features. Now we'll discuss the simulation and debug capabilities of our enhanced IEC package. Simulation allows you to test your program logic in our Seascape software without having a controller connected. It's a rich feature set. As part of the simulation, you get step-by-step execution, you get cycle-by-cycle execution, and you can set breakpoints and trace points. Now let's do a demo of some of the simulation capabilities. I have Seascape 9.9 Service Pack 4, and I've opened an IEC program. The first thing I want to show you is how to support Enhanced IEC. Firstly, you go to Tools and select Application Settings. Under Supported Program Types, make sure that the Support IEC Editor Programs checkbox and the Enhanced IEC Default Enable checkbox are checked. So when you create a new program, it asks you what type of logic language you want, and IEC will be a choice. By checking Enhanced IEC Default, if you're configuring a controller that supports Enhanced IEC, then Seascape will automatically utilize the Enhanced IEC feature set. You need to make sure that you're configuring a controller that supports Enhanced IEC. I've got an XL4, which supports Enhanced IEC. So with this program, I've got a simple bit of ladder logic. The ladder logic looks a little different than the advanced ladder from Horner. With the IEC package, we have very closely followed the IEC specification, so we've made it as standardized in appearance as possible, in addition to the standardized programming language and standardized function set. I've got a routine of some simple ladder logic. I've also got a structured text routine, and then I've got a subroutine that's written in structured text as well. Let's look at the ladder section. It's a start-stop circuit. We've got a timer where we are timing how long the motor is running, and then if it runs for a certain amount of time, we will automatically stop it. You will see some mapping has been done to some of these contacts because they are connected logically to a real-world I/O point. Let's test this program using the Start Simulation button here. I can press Start Simulation under the debug window as well. Once I press it, I now have status for each of the variables, true or false. For the timer encounter, I have the preset current value and the accumulator current value. And down here in my variable window, I have current values for all my variables as well. Let's see if we can start our motor. I'm going to push the start push button, so I do that by double clicking and hitting true. Nothing is happening. I've got power here, but no power there. Alright, so I'll let go of my start push button, and I'll make sure my e-stop circuit is passing power. I should be all set now. Let's double click here and hit true. Immediately I've got problems. My motor starts clicking on and off. It looks like this bit here is flipping on and off. I forgot to set the preset for my motor timer to a non-zero value, so that's not going to work. I'll set the start button to false again. I'll go down here to the variable list. I'll double click and I'll enter a value for that. Now my motor timer is set for a preset of 100, which is 10 seconds based on a 100 millisecond time base. Now let's see if this works as we expect. So I'll press the start button, and that's working. I'll let go of the start button. The motor is running, the time is counting up, and after 10 seconds we should have broken power. I can make sure the stops are working. We know the auto stop works, we know this stop works. That's just the normally closed contact, there's no issues there. So we fully debugged our ladder section. There's a lot more complicated sections of ladder that you could diagnose with the simulation feature. Let's go back and look at our loop here. I'll exit simulation mode. We have a simple variable called loop count, which we're incrementing from 0 to 100. When we hit 100, we fall out of the loop, and we set this variable to be equal to the output that we receive from this subroutine called stcalc. As soon as we make that calculation, we reset our loop counter to 0 and redo the whole thing. Let's go back into simulation, and let's go to the loop and watch what's happening. Our loop counter is incremented from 0 to 100. That all looks good. Let's go back to our slides and discuss additional features that we have with simulation. Let's start with breakpoints. Breakpoints are flags that set points in the program where your logic can be paused while you're executing. You can place them anywhere you choose, and they're fully supported for structured text and ladder. We also have a feature called Tracepoints, which are set points that cause a timestamp to be created every time that logic is executed. They provide solid evidence that the logic did execute. After you set these breakpoints and tracepoints, there's a series of commands you can use to customize how you work your way through your program. We'll start with the cycle by cycle button. When you're in simulation mode and you're in cycle by cycle mode, you are going to run until you get to a breakpoint. Single cycle mode is a way of executing a single scan. It will execute one scan through the entire program. Step in mode executes line by line as you press the button. There's the step over button and the step out button, which I'll demonstrate to show how they can assist in troubleshooting subroutines. We also have some debug windows. We have the breakpoint window where you can see the breakpoints and tracepoints that you've put in your program. We have a runtime window that shows you the timestamps for each of the tracepoints that you've hit during simulation mode. And we have a call stack window which shows the hierarchy of all called code. That can be useful for looking at how your instruction stacks up, or how your calls stack up from your main routines to your subroutines, and all that sort of thing. Now let's demonstrate the debug capabilities in Seascape. We'll look at breakpoints and tracepoints. Let's start with the breakpoints. I'll put a breakpoint somewhere here in our structured text loop. Okay, so we've looped from 0 to 100, the value of our loop counter equals 100. So now we fall out of the loop and execute this assignment command which calls the subroutine. I'll place my breakpoint here. I'll make sure the cursor is on that line. I'll right click and select Add Remove Breakpoint. So now I've put a breakpoint in the code. Let's go into simulation mode. It started executing the ladder logic because the routine is listed first, so it executes before the loop. As soon as it hit that breakpoint when our loop counter equaled 100, it paused. We're going to assign a value to the variable motor amp, which will be the result of a calculation that the subroutine makes on this variable motor AI. Motor AI currently has a value of 0. Let's give it a value of 100 so that the calculation will be a little more interesting. This value will be passed to the subroutine. When that subroutine gets executed, it will take the value, multiply it by 2.54, and then return that value. Let's run this again. I'll hit go. You can see that it made the calculation, and then it reset the loop counter to 0, and then counted back up to 100. I could go in here under Motor AI, set it to a different value, execute another loop through, and it would come up with a new result. Alright, now let's look at scan by scan capability. I'm executing a single cycle, which is a single logic scan. So I'll press this button, look at my loop counter. Every time I press this, I'm executing another scan and another cycle, and we're counting up towards 100 one at a time. It allows me to see what's happening on each loop as I'm counting up. So that's the single scan capability. Now let's look at the single instruction, or the line by line capability. Let's move line by line through the program with this button here. This is the step in button. I'll press that, and it moved me to the next thing it executed, which was the first line of ladder code. When I press the button, it goes through everything being executed line by line, so I can examine every individual instruction. The next thing I'll show you is how we control the stepping through our program when we've got a subroutine involved. Instead of hitting the scan button another 88 times, I'll go here to loop counter, change it to 99, and now I'll go line by line. Once I've gotten up to 100, I'm ready to fall out of my loop. So if I continue, I've fallen out of my loop. The next step is to enter the subroutine. Now if I press the step in button, it will step me into the subroutine. It will execute and then return after the point where the subroutine was called. Now let's do a complete cycle. Now we'll use a different approach to handling the subroutine. This time I'm going to press the step over command. I'll press the button. It didn't show me the subroutine at all, it just took me to the place where we returned from the subroutine. Alright, let's do this again, but with a new motor AI. Let's set this to a different value. Alright, I'll run the loop one more time. When it's done, I'll press step over. It executes the subroutine. You can tell by the motor amp value changing. Now let's look at the step out function. Let's change the value of motor AI. Alright, let's do another cycle, so we can get our loop back up to 100. Now let's press step in to get into the subroutine, and then let's press the step out function, which will step us through and then out of the subroutine, and then back into our ladder logic. So that was breakpoints. The next thing I will show you are tracepoints. But before I do that, I'll pull up some available windows that can be used when you're in debug mode. I'll go to the debug menu, and under debug windows, I'll enable all three of these. We're going to have a call stack window, a breakpoints window, and a runtime window. And once we're finished, at the bottom of the screen, we will have three windows: the breakpoints, the call stack, and the runtime. Alright, let's start with the breakpoints. So this window shows you the list of all the breakpoints and tracepoints that you have in your program. If you double click on one of them, it'll take you to the code where it's located. Now I'll show you the call stack window. Let's run through our loop to our breakpoint. Alright, there we go. It shows you where you are in the logic. So we're in the ST loop routine on line 4, and then if I go line by line, it shows me that I've called the calc subroutine. I'm on line 2, and that was called by the ST loop, line 4. So as I continue to step through that, I go back up to line 5. Call stack can be useful, especially if you have multiple levels of routines that you're dealing with. Now the last thing I'll discuss are tracepoints. Tracepoints are where you simply make a time and date stamp happen whenever that part of the logic is executed. So let's go into our loop, stcalc, and let's add a tracepoint right there on line 3. So I've got the cursor there, I'll right click and say add remove tracepoint. When I go back to the breakpoint window, you'll see that the breakpoint and the tracepoint that I put in are both listed here. Alright, now let's go to our runtime window. No timestamps here yet, but let's execute a cycle of our logic, cycle by cycle. Every time we call that subroutine, we pass that point in the logic, and even though we're not pausing in that subroutine, we have proof of exactly when we reach that particular trace point. Okay, so those are the debug windows that are available. Now let's exit simulation mode. There's a checkbox in the editor options within Seascape to enable array of structures. Let's go into Tools, and instead of going into Application Settings, let's go to Editor Options. And then under Compiler Options, we have a checkbox that says Support Array of Structures. If you want to support array of structures with IEC, you need to have that checkbox checked. However, this may cause some performance hits. So that was the demonstration for today. Thanks for attending today's tutorial. The Q&A session will begin shortly.
Okay, so thanks everybody. I hope everything in there was clear and it illustrated well just how powerful the debugging features are once we go to the Enhanced IEC packaged with Seascape. Got a couple of questions coming in. Is it possible to move the program variable window from the logic editing area? Yes, just take it and drag it and drop it up to the side of the screen, and your editing area becomes a complete not overwritten section at the center of the screen. Also been asked which language to use for different modules within the IEC. Which should I use? It really is a personal preference thing. As we say, the instruction list is what is now called deprecated. They don't recommend it for further development. It does produce pretty unreadable code, to be fair. Of the other languages, SFC is fairly unique and on its own in that it's not a language as such, but more a control notation package, which allows you to move the machine through different states. But between the others, function block, ladder, and ST, all down to yourselves really, and personal preferences. I tend to use a lot of function block where sequencing of blocks is necessary. For example, when working with the compact flash blocks or the removable media block, should I say. ST is great for doing calculations and manipulating data and data buffers. And ladder, if your preference is for that over function block, then go with ladder. Okay, so hope that's clear. Let's take a look at the upcoming webinars now. We were scheduled to the end of August. We've added all of September's now, or all but the last week. So let's take a look at those. As I say, we were scheduled up to the end of August with logic simulation today and advanced math functions next week. For September, we've now scheduled RTD thermocouples and thermistors, connecting those to the OCS and working with the data, connecting encoders to the OCS and working with encoders. Seascape security, so this is protecting your intellectual property in the OCS, so we can hide blocks away in the ladder and make sure people can't log in and upload your code without suitable credentials. And then getting started with IEC towards the end of September, the 23rd, where we'll kind of wind back to the start of what we covered today and actually go through what the languages are in a bit more detail and where you would use them, and also how you go about creating your first IEC program and getting that into the OCS. Okay, so thanks very much everybody for attending. I hope you've taken something from today's tutorial, and we'll see you all on another tutorial soon, I hope. Goodbye now.